Hello, everyone. We'll get started in just a couple minutes. All right, let's go ahead and get started. Welcome to our webinar today. My name is Justin D'Souza. I'm a quantitative specialist here at Statistics Solutions. During our webinar today, we'll be discussing how to conduct and interpret tests of differences. So I'm going to go through the presentation first, and at the end, we will do a question and answer session. So if you have any questions pertaining to today's topic, you can type your questions into the chat box or the question and answer box, and I will get to those questions at the end. I have a colleague today, Brittany, who will be assisting me with any questions about the services that our company provides. So you can type questions into the chat box about scheduling appointments or any questions about the services that we provide. Brittany can help you there. So yeah, just let us know if you have any questions. And we will be sending everyone a copy of the presentation along with a recording of the webinar. So I'll start out by giving an overview of the services that our company Statistics Solutions provides. Then we'll dive into today's topic, in which we'll discuss how to conduct tests of differences. So things like ANOVAs, t-tests, non-parametric tests, like Mann-Whitney tests. And I will show you a Intellectus demonstration, which is our company software, which is very intuitive, very efficient for running analyses and presenting the analyses in an APA write-up. And then we will conclude with a summary and the question and answer session. So our company, Statistics Solutions, provides assistance with virtually every part of the dissertation journey. So our company has both methodologists and we have literature review specialists. And we assist with both quantitative and qualitative topics. So we can help with topic development, editing your prospectus or concept papers. So in these couple sections, we can help you finalize your research questions and hypotheses, figure out what is your theoretical framework, help you identify a gap in the literature. Then we go into the proposal chapters, which usually consists of the introduction, literature review, and methodology. So there's some overlap there with a prospectus and concept paper. We can help figure out what analyses are best to address your research questions that would most likely go in your methodology, discussing limitations and assumptions, figuring out the best instrumentation you can use to address your questions. So we also help with IRB forms, data entry templates. We have a SurveyMonkey account in which we can help host your survey. We help with both quantitative and qualitative results chapters, PowerPoints for both proposal and final defenses, and journal publications, which usually involves taking your dissertation and condensing it down so it's adequate to submit to a journal publication. So if you have any questions about where we offer assistance and how that assistance is provided, you can give us a call at 727-442-4290. So we'll start out today with tests of differences. And before we actually dive into that topic, it's good to have a foundation for what types of statistics there are. So there are both parametric and non-parametric statistics. Parametric techniques are based on assumptions about your data. And usually this assumption is that your data follows a normal distribution. So I'm sure everyone here has at some point seen a perfect bell-shaped curve distribution, and that's a normal distribution. And when you run parametric techniques like Pretest or ANOVAs, one of the prerequisites is that your data follows a bell-shaped curve. Non-parametric techniques are not based on assumptions, meaning that the data can be collected from a sample that does not follow a specific distribution, meaning that a normal bell-shaped distribution is not usually required when you run non-parametric techniques. So a little more about the normality assumption. As we mentioned, parametric statistics assume that you follow a normal bell-shaped curve. And there are many ways to check for normality. So you may want to check with your committee. They may have a preference for which method you use. So there are tests of significance, like a Shapiro-Wilk test or a Kolmogorov-Smirnov test, in which your data is compared to a perfect bell-shaped curve. And if you have significance, then that means your data is different, significantly different than a bell-shaped curve. You can also look at skewness and kurtosis, in which there are specific value cutoffs that tell you if your data is skewed to the left or to the right, so it potentially deviates from normality. And then there are the visual methods that use scatter plots and histograms. So you can use normal PP or normal QQ plots. You can use histograms to look for a bell-shaped curve. Using one of these methods, some committees require multiple methods, but you have a few options here. If the data do not follow a normal distribution, then you can then shift to non-parametric techniques. Instead of sticking with the t-test, you could do a Mann-Whitney U-test, and we'll talk about that coming up. Another way to bypass violations of normality is having a large sample size. So I provided a citation here, Howell 2013, in which he states that violations of normality are not problematic when you have a sample size exceeding 50 cases. So 50 cases is doable for a lot of research. If you're doing a pre-test and post-test, maybe not so much. But for correlational analyses, or if you're comparing between males and females, 50 cases is oftentimes a doable sample size. So this is a strong justification for not meeting normality. Coming back to the second bullet point, I have a preference for using tests of significance. So I like doing Shapiro-Wilk or Kolmogorov-Smirnov tests because looking at scatter plots and histograms is a very subjective interpretation. Everybody's going to interpret it slightly differently, whereas with these Shapiro-Wilk and Kolmogorov-Smirnov tests, it's an objective finding. Yes, your data follows normality, or no, it does not. So the first test of differences that we'll look at is comparing between two groups. And the parametric technique for this analysis is an independent sample t-test. So this is appropriate when you're testing for a continuous or interval ratio variable between two groups. For instance, if I'm looking at differences in GPA or maybe job satisfaction between males and females, that's when you run an independent sample t-test. Now, say you verify for normality and the assumption is not supported, then you can run a Mann-Whitney U-test as a backup. So a Mann-Whitney U is the non-parametric alternative to a t-test. A Mann-Whitney U can also be used if you have ordinal data instead of continuous data. So if you're just looking at differences in one Likert scale item, something that goes from strongly agree down to strongly disagree, that is an ordinal item on its own. So that's when you can do a Mann-Whitney U-test. So how do you set up an independent sample t-test or a Mann-Whitney U-test? You first need to have an independent variable that is dichotomous. So dichotomous essentially meaning binary. It has only two possibilities. Examples include gender or groups in an experimental study, like treatment and control groups. You need to have a continuous or ordinal dependent variable. And I provided a couple hyperlinks here. Statistics Layered is a very popular website used now with committees because they identify specifically what assumptions should be checked. So just for example, let's take a look at this one. This is the independent t-test, and they connect a lot of their findings with using SPSS, which is a statistical software. So if you scroll down a little bit, you'll see all the assumptions of a t-test listed over here. Okay, so you have the key one here is normality that we discussed. So you need to have a normal distribution. There are other assumptions, but when doing parametric techniques, this is really the most important one, I would say. Okay. Okay, and then we have a link for Mann-Whitney U-test here, and then you can run your analysis in Intellectus Statistics. Let me show you Intellectus Statistics, our company software. So this is what it looks like, and I have a sample spreadsheet uploaded already. So click Load Project, where it takes you. And you can see that we have here, this was an experimental study done among nurses. The nurses were put into 3 groups, either control, treatment A, or treatment B. And the purpose of this was to test for self-efficacy in hospitals. So the nurses did a pre-test, they did a post-test, and then they did a 6-month follow-up following the training. And we have final scores for all of these: pre-test, post-test, follow-up. And you can see in Intellectus, you can do many data management functions. You can recode data from continuous to scale to nominal or ordinal. You can remove outliers. You can impute missing data, reverse code, create variables using composite scores, and you can even download it again. So if I download it right here, it's now presented in Excel format. Okay, so from here, we can go to analyses, and I already ran a couple things on this spreadsheet. We'll do it from scratch. So for an independent t-test, we'll go to the t-test family and independent sample t-test. So your dependent variable is the variable that you're testing for differences between. That will be, for instance, just pre-test scores. And the independent variable is your dichotomous variable. So the variable that has only two possibilities, in this case, we'll look at gender. And then you click calculate, and Intellectus gives you a full APA write-up. So we've verified all the findings in SPSS. We cross-referenced findings and they all match, but it gives you an automatic interpretation. So the first assumption that is checked is normality. And based on the findings of the Shapiro-Wilk, normality was supported for both pretest male category and pretest female category. Then we look at homogeneity of variance, which is another assumption of a t-test, and this was also supported. For these two statistical tests, it's a rare time in statistics, but you hope for non-significance, meaning you hope for a p-value greater than 0.05 with tests. And then we come down to the t-test itself. Okay, so we can see, is there a significant difference in pre-test self-efficacy scores between males and females? And we can see that males had higher mean scores than females, but the p-value here is not significant. So while there is a difference, it's not a significant difference. Okay, so that's an independent t-test. Hypothetically, say that one of the assumptions was not met here. We can run a non-parametric test, which in this case is a Mann-Whitney test. Okay, so we'll put our dependent variable as pretest again, and our independent is gender. Okay, so we can see for the Mann-Whitney test, you don't have a normality check, you don't have a homogeneity of variance check. There are no strict assumptions to check for a Mann-Whitney test. And the p-value, again, is non-significant. So this is oftentimes, if you run a t-test and the assumptions are not met, the Mann-Whitney can be used as an alternative or a backup. Your committee may want it as an alternative in which you present both the t-test and the Mann-Whitney test, or it's just the alternative. You don't present the t-test, just stick with the Mann-Whitney test. It's really committee specific. But we found the same statistical findings, non-significance for both. Okay, so the next test family is testing for differences between two or more groups. So similar to what we just looked at, but say you had three groups of comparison as opposed to just male and female per gender. If you had ethnicity instead, that's what you can do with an ANOVA or a MANOVA or a Kruskal-Wallis test. So an ANOVA stands for an analysis of variance, and it's used when you're testing for differences in one continuous variable between two or more groups. A MANOVA is testing for differences in multiple continuous variables between two or more groups. And then the non-parametric alternative to this is a Kruskal-Wallis test. And a Kruskal-Wallis is the non-parametric version to an ANOVA. Unfortunately, there isn't a non-parametric version to a MANOVA. You just have to do multiple Kruskal-Wallis tests instead. So you set this up exactly the same way as the t-test. You have the variable of interest that you want to assess for differences in. That's your dependent variable. Your independent variable, very similar to gender in the previous example. Your independent is the variable that has groups. So ethnicity, maybe blood type or political party. These can have 2 or more possibilities. And you need to have at least 1 or more continuous or ordinal dependent variables for your outcome. Again, we have hyperlinks here that describe the assumptions for an ANOVA, MANOVA, and Kruskal-Wallis, and then you can run your analysis and intellect this. So for an ANOVA, what I'll do here is let's test for differences in post-test scores based on treatment. So if someone was in control, treatment A, or treatment B. So we'll go to analyses and ANOVA. Exactly the same setup as the t-test. So we'll do a dependent variable of post-test score, and then our independent will be treatment. We'll click calculate. And again, it's going to verify for statistical assumptions, and normality was met with the Shapiro-Wilk test. And just to show you, I mentioned the Kolmogorov-Smirnov test. We do have that over here under assumptions, Kolmogorov-Smirnov. So we have multiple ways of checking for normality, but this is built in to the ANOVA, the Shapiro-Wilk. Then we have homogeneity of variance, which is also supported here. Then we come down and we can see, are there differences in post-test scores based on treatment group? The finding of this p-value is below 0.05, which indicates that yes, there are significant differences in self-efficacy post-test scores based on treatment. Okay, and then you can see the mean scores down here. So it looks like treatment B had the highest mean score in comparison to the control group, and even treatment A had higher scores in comparison to the control group. And then we have a bar chart to represent the findings. The non-parametric alternative to this is a Kruskal-Wallis. You just do the same procedure, post-test and treatment. Okay, so there are times where we found significance for the ANOVA, but the math is quite a bit different when you do a Kruskal-Wallis test. And this is an example where we didn't need to do a Kruskal-Wallis. I'm just kind of doing it to illustrate. We didn't need to do a Kruskal-Wallis because the assumptions of the ANOVA were met. We did find normality to be supported, so we didn't really need to do a Kruskal-Wallis in this case. But as you can see, I guess this is a good example for me to show because the findings do contradict what the ANOVA found just slightly. So this p-value is just over that threshold of 0.05 significance, meaning that while there may be a difference, it's not a significant difference. Okay. Now we can test for differences in a variable between 2 points in time. So we're shifting from a causal comparative design to a longitudinal design. So this is used when you are matching data. Very similar to the spreadsheet we've been looking at. So you have a pretest, you administer an intervention, and you bring back the same sample to take a post-test. So this is when you run paired t-tests or Wilcoxon-Signed rank tests. So the paired t-test, also called a dependent sample t-test, is used when you're testing differences in a continuous variable between 2 points in time. So very important that the data are matched when you do this. So whether you give participants an ID number that they input on the survey, they need to come back for the post-test for this particular analysis to work. And then the non-parametric alternative to the paired t-test is a Wilcoxon-Signed rank test. That can be used when the data doesn't follow a normal distribution. So how do you set this one up? You have to have one dependent variable that's measured 2 times, specifically only 2 times. And then you can check for the assumptions, and we have the hyperlinks here. And then you can jump into Intellectus. So what we can test is there a difference between pre-test and post-test? So you can see how the data are matched. This one row of data, this one person who was in the control group completed the pre-test survey, and then they completed the post-test survey, and they have both a pre-test and post-test score. We'll go to analyses. And this is also under the t-test family. We'll go to paired sample t-test. And variable 1 will be the pre-test measurement. And variable 2 will be the post-test measurement. Okay, so built into the software again, we have a Shapiro-Wilk test that is going to check for normality. And the assumption of normality was met, meaning that we can continue with the paired t-test. As we come down here, we can see the pre-test measurement was 4.38 and the post-test was 5.75. Our p-value is below 0.05, showing that there is a significant improvement in self-efficacy after the first intervention. And then we have a bar chart that shows that increase. And then hypothetically, say normality was not supported, then you may want to run a non-parametric, which is a Wilcoxon-Signed rank. You hover your mouse over, as you can see, that kind of describes what it's doing. So test the differences in 2 paired ordinal or scale level dependent variables, paired being the key word there. It's matched between pre and post. We have pre-test and post-test. I do see we have some questions coming in. I will be answering those at the end of the webinar. Okay, and then this is the Wilcoxon-Signed rank. If normality had not been supported, this is what you would want to run. And our p-value is still significant, showing that there is a significant improvement in self-efficacy. Okay, so we finished those ones, paired t-test, Wilcoxon. And then we take that idea of differences over time, but instead of just pre-test, post-test, we can introduce a third time point, third or more. This is when you can do a repeated measures ANOVA, which is used when you're testing for differences in 3 or more points in time. Very much like the spreadsheet that we have a pre-test, post-test, and a 6-month follow-up. And then the Friedman ANOVA be your non-parametric alternative. We won't go through Intellectus for that one because it's very similar to the paired t-test that we did. So to run this test, you just need to have a variable that's measured 3 or more times. Really important that you match the participants again. So the same people take pre-test, post-test, and follow-up. So you have to account for potential attrition. When you have that many time points, you can't always expect the participants to return for the follow-ups. So it's good to overestimate for your sample size. I would aim higher than you would normally need. Then we have the links for the assumptions. And this test family is really combining everything that we've looked at today. So if you're looking at differences between groups and time simultaneously, what do? You can run a mixed model ANOVA. So a mixed model ANOVA is looking at three things. It's looking at differences between groups, it's looking at differences over time, and it's looking at the interaction effect. So are there differences between treatment and control and pre-test, post-test simultaneously? And for the non-parametric technique, there is not one. There is not a non-parametric alternative to this, unfortunately. So if you do test for normality and it's not met, you can, hopefully you have a large sample size to which you can justify proceeding with a mixed model ANOVA, or you can interpret the level of caution. Okay, so how do you set this up? You set up a mixed model ANOVA, you need to have an independent grouping variable, such as treatment and control. And then you need to have one continuous dependent variable that's measured at least 2 times. Here's the hyperlink to look at a mixed model ANOVA and what assumptions should be verified. And then you can run your analysis in Intellectus. So let's take a look at this one. So again, remember we have 3 points in time, pre-test, post-test, follow-up, and we have a grouping variable, treatment, so control, treatment A, treatment B. We'll go to analyses, and under the ANOVA family, select mixed model ANOVA. So your within subject effect is essentially your dependent variables that are measured multiple times, pre-test, post-test, follow-up. Your between subjects effect is your grouping variable, so that will be treatment. And we click calculate. First, it checks for normality. We can see that the assumption is supported. Then it checks for homoscedasticity, which is like homogeneity of variance, but checked visually. And hopefully you see random scatter in your scatter plot, which we do see here. Then we check for sphericity, which is making sure that the variance in self-efficacy is approximately equal between pre, post, and follow-up. And then we look at the 3 effects that I mentioned before. So there's the between effect. Are there differences by group? Treatment A, treatment B, and control. And we have an associated p-value for that. So this is just over that significance threshold, showing that collectively there are not differences between the groups. Then we have our within effect, within factor, which is time. Is there a difference between pre-test, post-test, follow-up, regardless of what group people fall into? This is significant. And then we have, excuse me, and then we have our interaction effect. Is there a difference between pre-test, post-test, follow-up by treatment and control? Okay. And this was significant as well. Again, then we have pairwise comparisons down here. So you can see specifically for treatment A, is there a difference between pre-test and follow-up? Yes. Is there a difference between pre-test and post-test? No. So it looks like over 2 interventions is where we're finding a significant difference between pre-test and follow-up. And then for treatment B, we are seeing a significant difference between pre-test and post-test, and we're seeing a significant difference between pre-test and follow-up. Okay, and then the control group, we found no differences whatsoever, which is to be expected. Okay, so in summary, you want to, first you need to pinpoint that you're using a quasi-experimental or true experimental design in which testing for differences is really what you want to look for. So you're not running correlations or regressions. you're looking at differences. So you most likely need to run a t-test or an ANOVA. Then you want to identify if you have independent grouping variables. So we looked at gender before, we looked at ethnicity, we looked at treatment A, treatment B, control. So you need to know if you have partitions into groups. Then identify if you're looking to test for differences between groups. Are you looking to test for differences over time, or are you using both? And then once you collect your data, you can use intellective statistics to analyze and present your interpretation in APA format. So that concludes our webinar. I'll now open the panel for questions. We will send everyone a copy of the recording. If you have any questions about the services we provide, you can call us at 727-442-4290, or you can email us at info@statisticsolutions.com. All right, do we have any questions? Okay, so yeah, we had a question. Can you run an ANOVA and put all the independent variables in at the same time? Yes, you can. So let me show you that. So if I go to ANOVA and say we're looking at post-test scores, and instead of only looking at treatment, we can put gender in as well. So treatment and gender. We only have two options in this spreadsheet, but if you had multiple grouping variables, you could put multiple variables in. Okay, so we click calculate, and you can see there's going to be separate effects run for both treatment and gender here. So you have an associated p-value. Are there differences in self-efficacy based on treatment? Yes, we can see that there are. And then are there differences by gender? No, there are not. Okay, we have a question. When using an ANOVA in a KAP study, I think KAP is knowledge, attitude, practice, if I'm not mistaken. Do you use the raw knowledge scores of the participants, or do you use the good versus bad knowledge score? It depends what survey you're using. Most likely you want to use raw knowledge scores, especially if you're doing an ANOVA, because in ANOVA you need to have a specific score associated with it as your dependent variable. You don't want to have a dichotomous variable such as good or bad. You want to have one overall score. So I would say use the raw knowledge score. And then we have a follow-up question. It says, if doing an ANOVA test for knowledge, attitude, practice, what does the test of between subjects for each component mean? I'm assuming with the KAP, with the survey that you're using, there's both, there's one score for knowledge, there's one score for attitude, and there's one score for practice. Which means you could run a separate ANOVA for each of those components. Now you need to have a grouping variable as well. Okay, so you need to have something that you're testing for differences between, whether that's gender, whether you're doing an experimental study and you have treatment and control groups. To do an ANOVA, you need to have a grouping variable. I'm not sure if that's identified in what you're doing right now. But in order to test for differences between groups, you need to have an independent variable. Okay, does that make sense? Yep, we will be sending everyone a copy of the PowerPoint and a recording of the webinar. you have any other questions about intellectus or the topic for today? Yes, so I would put all the independent variables in for the test between subjects. Yes, you can put all the variables in your independent box right here. So similar to how I just did treatment and gender, you can input them all at once. When would you use regression modeling versus ANOVA? That's a great question. So regression modeling, the key word there is predictive effect, or when you're trying to predict an outcome. So it's usually when you have a series of independent variables and you're trying to see how it predicts an outcome. And when you do a regression model, you can have predictors that are numeric, like GPA, for instance. You can have grouping variables such as ethnicity or gender. When you do an ANOVA, you need to have distinct groups, and the purpose of an ANOVA is to test for differences between groups. So regression is trying to predict, ANOVA is looking at differences between groups. That's the basic distinction. And that usually comes down to your research design. So if you're planning to use regression modeling, your research design is probably quantitative and correlational, or quantitative and predictive. Whereas if you're using ANOVAs, it's most likely quantitative, quasi-experimental, or causal comparative, or true experimental. So if you're doing a treatment and control study, pre-test, post-test, random assignment of people into treatment and control groups, then that's a true experimental design. All right, very good. Do we have any other questions? We'll refer you as well to our company website where you can take a look at the upcoming webinars we'll be conducting. So it looks like tomorrow we have a literature review webinar, as well as a qualitative methodology webinar. So my colleagues, Tom and Rachel, will be doing those. And my colleague, David, will be doing a quantitative methodology. And that will be on Friday, or sorry, not Friday, that'll be on Wednesday, 17th. And then we'll be doing a quantitative results chapter webinar on Thursday. Yeah, so a lot of good methods and results chapter discussion. If you join the webinar today, maybe the qualitative one is not of utmost importance unless you're doing a mixed method study. But definitely check it out. It's great. A lot of the information, regardless of what you're doing, quantitative or qualitative, the information overlaps between the two designs. So I would check it out. Okay, so we had a follow-up question on the regression question. So you put all the independent variables at the same time and use, for example, the raw knowledge score. Yes, that's right. Yeah, so when you do a regression, you can only have one dependent variable. So I don't think you couldn't put good versus bad knowledge in one regression. You would have to do two separate regressions potentially. But it's my instinct that you don't need to do good versus bad knowledge at all. There should be one overall knowledge score, and that can be your dependent variable. You're very welcome. Thanks for joining us. All right, do we have any final questions? Should also mention that on our company website, you can view a webinar archive as well. So you can see the past presentations we've done, and you can watch the video for all of them. Okay. So we've covered a variety of topics from data cleaning and data management, chapter by chapter webinars, and even specifics down to developing research questions and hypotheses. So check out those resources if you have any questions. All right, looks like we may be done with questions. Thanks for joining us, everyone. We'll send you a copy of the presentation and the webinar. Let us know if you have hit a roadblock in your dissertation. You can give us a call or email us, and come join us for future webinars. We'll be in touch. Have a great evening.